Hi everyone. I just first mentioned to thank the organizers of this session and this conference for giving me the opportunity to present in such a beautiful city and this university. Well, my talk will be on computing boundaries and local mixture models. This is a joint work with my supervisor, Professor Paul Marriott. I'm going to start with some outline and discuss some review of influence of boundaries on parameter inference and statistical analysis. One of the examples was the previous talk that when we include boundaries, there are a whole bunch of, like in multinomial distribution, there are a whole bunch of problems shows up and we cannot use the regular analysis. And then I'll introduce local mixture models and then their parameter their boundary of the parameter spaces that they include two types of boundaries, hard boundaries and soft boundaries. And then I use some rather simple classic geometric methods to approximate these boundaries. Well, first some review. When the parameter space in a statistical model includes boundaries, at least one of those cases can happen. For example, maximum likelihood estimator, which was one of the most, popular method of inference may not exist. And if it doesn't exist, then we need to find the boundary point as a maximizing point for likelihood function, which in order to do that, we need to characterize the whole boundary or understand the geometry of the boundary. Or MLE might exist, but if it is close to the boundary, it may not have those regularity conditions, such as normality. There are lots of examples like binomial distribution or the general form of it, multinomial distribution that you guys saw in the previous talk. If we include the boundaries, there are a whole bunch of problems in it. And then logistic regression and contingency tables, which they are discussed by Geyer, that how non-existence of maximum likelihood estimator may affect the confidence interval and also hypothesis testing. Also, the log linear models are discussed by Rinaldo and Feinberg in 2009 that their boundary are pretty complicated and maximum likelihood estimator just exists when the observed sufficient statistics lies inside the interior of the parameter space. And their parameter spaces are pretty complicated, like high dimensional polytopes or high dimensional polyhedral cones or a mixture of them. In general, as discussed by many researchers, computing boundaries is a really hard job, but there are lots of mathematical results that you can classify them in these two directions. You can approximate the boundary by a polytope. For example, you can generate a set of random points from the boundary, and then you can construct a convex hull of those boundaries, then you end up with a polytope approximation, or you can use these works by, you can approximate by smooth surfaces based on the methods developed in these seminal papers. But right now, I'm gonna move on to the focus of this talk, which are the local mixture models. If you consider a density function f of x belonging to exponential family, here parameterized by mu, which is mean, it can be any general parameterization. You can extend this family by adding these terms and generate a much more extended model and flexible model called local mixture model, G. In terms of geometry, you can just consider that as a simple example of the fiber bundle structure that Professor Amari generated. For example, you can consider this function as a curve inside the full exponential family and then add these terms as fibers, which these fibers are actually, in terms of geometry, they're -1 flat fibers. But here we are interested in a subset of those fibers because lambdas are restricted to these subset, which I'm going to discuss what is like these subset of parameter spaces. They have lots of great advantages. That's why we need to know their boundaries. For example, they are always identifiable. Their parameterization is orthogonal in case you want to do some profile likelihood maximization. Or at each fiber, the likelihood is log concave. These parameter space is convex. Two great properties if you want to do like convex optimization for finding maximum likelihood. And also, the original intention of introducing these models was to approximate this type of mixture. If you have this type of mixture model, which is a infinite dimensional model because Q, the key distribution, is not known, you need to, what we can do, we can just restrict this Q to a small interval M and call it, as they call it, localizing mixture model. And you can approximate this by a local mixture model to an arbitrary order. Well, it turns out after this approximation, turns out that local mixture model are also can be more richer than mixture model in the sense that if you compare a local mixture model to an unmixed model with the same mean value, you can produce even lower dispersion. But we know as a general rule, the mixture model just produce higher dispersion. Now look at this example. For example, for a normal density function, the extended model has these form. PJs, they're polynomials of order J. And if we fix K, which is called the order of a local mixture model at 4, now I want to just argue that why these lambdas on these parameters spaces are important. The lambdas are not just nuisance parameters, they have a nice interpretation. For example, lambda 2 contributes to the variance. These terms are the central moments of the extended model. If lambda 2 is positive, we have an over-dispersed model. If it's negative, we have lower dispersed model. We know that skewness for the base normal distribution is 0, so it's always symmetric, but lambda 3, if it's not 0, it adds positive or negative skewness, and so on. Or another way of verbalizing that is that in approximating such a mixture, when Q is not known but is just restricted to some small interval M, lambdas represent the moments or pseudo-moments of this Q distribution. Well, so far I've been just talking about the advantages of these models, but there are two disadvantages comes at a cost. The costs are two types of boundaries that they restrict the parameter spaces. First called hard boundary, which is the boundary of this parameter space, and the second called soft boundaries, which if you wanna our local mixture model not to be richer than mixture model and follows exactly, at least locally, behavior of mixture models in terms of moment structure, we need to restrict it with these boundaries too. While we discuss in this talk just two working examples, Poisson and normal as discrete and continuous distributions in exponential families, which can be quite representative for the whole family. I fixed K, the order at 4. I mean, it doesn't restrict any generality of the analysis, but we fix K at 4 because adding just the order in terms to local mixture model, it doesn't add significantly to the inference power of the model. Here are the definitions of the hard and soft boundary to spell them out. The hard boundary, which guarantees positivity, has this form, set of all lambdas that they're positive for all those equations. Like if you look at it in terms of geometry, this boundary has a form of intersection of a infinite number of the half spaces. Each half space has a boundary hyperplane, which is determined by a value x, which is inside the sample space of the base density function. And then the hard boundary is a boundary of this convex parameter space. This is the general result in Berger's Geometry 1 book, that since it's the intersection of these half spaces, it is also convex. And the boundary is constructed by a set of those hyperplanes if we put this equality to this inequality to be equality to 0. For the soft boundaries, defined for any density function f, define these moment vectors. Just consider the first k vectors of the density function f and put them beside each other, make a vector, and then each of these moments, they depend on this value m. Now construct this set, the convex hull of all those vectors as points for all mu inside a compact set interval m. Then the boundary of this convex hull is called soft boundaries. If we restrict lambda such that this vector for the extended model lies inside this convex hull, it is pretty intuitive that it mimics the behavior of general mixture models. Now the first example about the Poisson, look at the set of the half spaces. The set of half spaces are determined by non-negative integers. So we sort of have an infinite countable number of half spaces, and as a result, infinite number of supporting planes that they construct the boundaries. But since this is a discrete, this x is discrete value, we sort of expect discreteness in the boundary. So we see some, if we plot the two-dimensional section, cross-section of these three-dimensional parameter space, we end up with these kind of polygons or two-dimensional polytopes, which they have active boundary planes, and then they have some, as you may say, inactive or redundant boundaries, which they are plotted by dashed lines. We can end up finding a limiting behavior for these boundary planes, which essentially we can show something, a result like that, that this boundary can be approximated by a convex polytope where it has a finite number of faces, which is much easier to deal with than a polytope or another object with infinite number of faces. Now, I move to the normal distribution. Look at the normal distribution. The set of half spaces, it is infinite, but it is not countable anymore. So y belongs to R. We sort of, based on this, since y is continuous variable, we sort of expect some type of continuity in the boundary, not discreteness. This short animation, if it plays, it shows the behavior of the boundary. There are two-dimensional cross-sections of the boundary. If you look at it, we sort of see, we type of see the smoothness of the boundary, which is not a polytope type. So it is not, there is no way to approximate this boundary by a polytope as close as possible. We always lose a lot in terms of precision. Here, so what we need to do, we need some more smooth geometric objects in order to apply them here to compute these boundaries. It turns out that there are some classic geometric objects that we can use here, which they're called ruled surfaces and developable surfaces. I'm just going to review them for a second. That a ruled surface is a special type of surface that can be parameterized by a smooth curve, smooth differentiable curve as a function of x, and a set of vectors or lines, straight lines attached to this curve at each point. Then we can parameterize the whole surface by x and this gamma, which is the length of each vector at each point. A special type of ruled surfaces that we have in 3 dimensions, they are developable surfaces where these 3 vectors are actually coplanar. There are some classic examples, a cylinder and a cone, they're ruled surface and developable surface, but this later object, for obvious reason, there's a curvature here, it's a ruled surface, but it cannot be considered as developable surface. Another type of ruled surfaces that we're going to use here for computing the boundaries in normal local mixture are the envelope of a family of one-parameter planes. Imagine that you have a family of infinite planes that they are determined by one parameter. For example, A is a set of whole bunch of planes where x belongs to R as a parameter that determine the normal vector and also the intercept of these planes. So if we have x, we totally know that what is the plane like, what direction. Then these planes are not all, if they're not all parallel, which exclude that the case that they're all parallel to each other, they have an intersecting line. The intersection line, which is called characteristic line of the envelope or rolling of the envelope, that they are obtained by solving these 2 simple equations. And the characteristics line, the union of them, if we put them all beside each other, they construct a surface in 3 dimensions, and that surface is the envelope of the set of these set of planes. This envelope is also turned out to be a developable surface, as it can be parameterized as a ruled surface by 2 parameters. Now look at the same analysis for the hard boundary of local mixture models. The hard boundary of local mixture model has this set of boundary planes, which is the infinite number of the planes. And if we calculate the rollings, we have the boundary in this type. These lines are the rolling or characteristics line, and this red highlighted part is the active boundary. And this is the 2-dimensional cross-section of the parameter space, which shows it is smooth. I just need one more second to discuss these soft boundaries. For the soft boundaries, what we need to do, if you remember, this is the recap that we defined this vector of the moments. We need to construct a convex hull of all those points for all value of m inside, all value of mu inside the compact set, compact interval m. For normal distribution, fix sigma, and let k to be equal to just for visualization purposes. We just want to see the pictures. Then this curve, these functions, these vectors as a point beside each other, they construct a space curve. In this is the space curve that is constructed for every values of m. It has a torsion and curvature. If you want to construct the convex hull of this, you need to draw all these lines from each of the ending points to each point of the curve. Then you have such a surface and another surface at this side, the pink one. Then you have constructed the convex hull by two surfaces, which they are constructed by a space smooth curve and a two surfaces which they are. And this is the last slide which just show the parameterization of these ruled surfaces also, that it can be parameterized similar to by two surfaces, which is constructed by one smooth curve and a set of lines which they are attached from each side of the ending points. Just a quick summary, I would say that the takeaway of this talk would be if we have complicated models and we want to use the advantages and their properties, these complicated models, if they have boundaries included, we need to understand those boundaries. This is also the examples that we showed here. They show that there are some discrete and also continuous aspects of these models. And the two examples that we showed, Poisson and normal, they can be pretty representative for the whole exponential families. They are not specific. For example, for binomial distribution, we have the same structure as Poisson. And for exponential continuous distributions, we have sort of the same structure as normal. Also, it is really interesting to design information geometric methods for optimization algorithms to search all those surfaces in order to find maximizing point when maximum likely estimated does not exist. For continuous ones, we have such algorithms, and for discrete ones, I think Feinberg and Rinaldo, they have designed such algorithms. Thank you so much. If there are any comments and questions,
Thank you very much.